So good afternoon everyone. However many of you out there. Welcome to another section of ELEC3208 and today we're going to talk about power amplifiers. So right at the beginning of the course I put this slide up and showed the sort of things that we're going to be dealing with in this course, and we've done this bit: signals and sensors, we've done amplifiers, we've done filters, we've done power supplies now, or as much as we're going to do anyway. And now we're going to look a little bit more at power amplifiers before moving on to look at A to D and D to A. And then Kaylee will come back and talk to you about PLLs and systems like that, and voltage controlled amplifiers and things that will go into that, because that's a very powerful system block. And then Ruomeng will come and talk about noise and how to make low noise designs and how to calculate the noise in systems. And we're hopefully going to do a little bit of work on this, but we're getting a bit behind in time, so we'll probably cut this down a little bit because EMC is all changing since we've left the EU. The rules for marking of electronic components and the standards are changing, and I'm not completely sure what they are at the moment, so might be best not to tell you too much about that because it's all out of date and changing. Anyway, power amplifiers today. So you can see from the previous diagram, once we've taken a small signal in, amplified it, taken it into a digital system, done something with it, we might then want to output that and do something useful with it, and that requires some power. And as always, once we start to operate at higher powers, we tend to get quite excited about efficiency, because any wasted power always ends up as heat, and when things get hot they tend to break or manifest itself as a high running cost. And so particularly sort of for RF radio systems, so TV and radio, and particularly with the advent of digital TV, amplifiers tend to be not very efficient. In the old days of analog TV, we used to have megawatt transmitters, and there weren't many of them, and it was relatively easy to keep them relatively efficient because there weren't many of them, so you could spend some money on them. With the advent of digital, there's quite a lot of TV transmitters around now because they tend to be operating in the low kilowatt range, and so there's a fair few of them around, so the cost of transmitters can go up because there's a lot more of them basically. And because there's a lot more of them as well, we want them to be efficient, and we know that TV transmitters are very inefficient. It's one of the downsides of digital transmission. Usually digital is very efficient for most things, but in terms of transmission for radio signals, it's not great. Get lots more channels in there, but power isn't great. And as we progress in this part of the course, we'll also look at what happens at temperature, and it doesn't take much to affect the operation of a transistor. And if we just raise the junction temperature to above about 150 degrees C, we find that transistors start to get a bit unreliable, and much higher temperatures, or running at higher temperatures, will actually destroy the device. So controlling heat becomes important, particularly when there are lots of watts whizzing around your system. So you can either do it by good design or by cooling it somehow. So power amplifiers mainly are broken down into operating classes, and people keep inventing new classes, but there are some main ones, and they're not terribly imaginatively named. We've got Class A, which we'll talk about in some detail, Class AB, Class B, and we'll talk a little bit about Class D amplifiers as well. So you notice there's a C missing. There are Class C amplifiers, but they tend to be used in quite specialist applications in radio systems. So we'll briefly touch upon it so you get some idea of what they're doing, but we won't go into much detail of them. It's not really what we're about. So to understand what's going on in these classes, and it always surprises me that people haven't heard about these classes. I keep asking every year, well, I've done it up till now, this year anyway, and people have told me, no, we haven't done classes, we don't know what they are. So I'm assuming that's the case for this year as well. But a Class A amplifier will conduct throughout the cycle, which means that when there is no signal applied to the input of the amplifier, there will be a bias current flowing through the stage. And if there is bias current or any kind of current flowing through some system, there will be some resistance and there will be some dissipation of energy. So this implies that there will be wasted power, there will be energy being dissipated even when no signal is applied, because there's a current flowing through it to bias it. And in fact it turns out to be a pretty bad case when no signal is being applied, as we'll hopefully see in a few minutes. So to get some idea of what's going on, so this is the collector current, the output current of this amplifier. In Class A, with an input sine wave coming in, the collector current is always going on, and you can see, so this is for an input, so you can see that for no input, if we had a flat line on here, then IC would be a finite value, and this is what leads to dissipation for no signal coming in, because there's a collector current flowing under all conditions, or under zero signal conditions anyway. So Class B takes us, and this is a simplified version of Class B, takes us to the point where it only conducts for half a cycle. And so when no signal's coming in, there'll be no collector current flowing, and then it will conduct on the other half again. And so for Class B, we'd have to have two amplifiers, one conducting in the positive cycle and one conducting in the negative cycle, and we join them together. But when there's no signal coming, each of these amplifiers has no bias current flowing through it. And we'll look at that in some detail going forward as well. Now, it's never as perfect as this, because you always need a small amount of voltage to turn on a transistor stage. So although it's been drawn here as having a good joined up sine wave, there's actually what's called the crossover distortion at the zero signal input point. So there'll be a little step, just as this one is say turning off, but this one just hasn't quite got enough voltage to turn on yet. It needs 0.7 volts if input before it starts to go, so there'll be a little bit of distortion here, and we'll look at that. So Class AB is a sort of a combination of these two, where we're trying to get the Class A stage biased just at the point of conduction. So there'll be a very, very small amount of collector current flowing, and so we can eliminate this crossover distortion, and the reason for that will become clear as we go forward as well. So Class A is conducting throughout the whole cycle, one transistor, and purists will tell you this is the best type of amplifier. Class B is where it only conducts for half the cycle, and you need two of them to get the whole cycle conducting. And Class AB is a combination of these two, which is trying to improve the distortion characteristics of the Class B. So Class C, just mentioned for completeness here, actually conducts for much less than half a cycle, which is sort of the opposite of the Class B, Class AB rather. And it's usually driven at a resonance, drives a resonance circuit. So here, if you see in the collector of this amplifier, we've got a resonance circuit, an L and a C, and that will just bounce quite happily. And that's tuned to operate at a certain frequency. And what happens is that the input signal here will, let me get a pen. The input signal is going up and down like that. This transistor doesn't conduct for a whole cycle, and what you actually get out of the conduction of this is like a little kick, and then nothing for a while, then a little kick. Oops, okay, like that. So it's just little pulses being driven to this, and this kicks this circuit, which then will oscillate down, and then you kick it again. So if you leave it long enough, it will then kick up, and then it'll oscillate down. So if you kick it quickly enough, you end up with it oscillating and just doing this across its natural frequency. So as long as this is close to the resonant frequency of this, you can just kick it with little bits of energy and it will oscillate big time. So it's not much good for generating varying frequencies, but if you're generating carrier for RF or something, then it's quite an efficient way of doing it. And then class D is basically pulse width modulation, which we talked about in the last lecture. And so we have a digital drive signal, so this is the triangle wave generator and our varying input signals, so we get pulse width modulation out. We use that to switch to a high voltage, so you get a big version out that's just been switched, and then you put that through a low pass filter, and it takes the average of this, which is obviously continuing varying, and gives you back your sine wave, but at a much higher amplitude because we've gone through a switching gate. So this is a sort of a logic switching, almost a logic switching circuit, but driven by much higher voltages at this point here and this point here. So we've taken a small one, made it bigger by switching amplified, so it's just turning it on and off, and then we just filter that and take the average, and that gives us a bigger sine wave. So there's some quite clever techniques that people have tried over the years. These class Ds are becoming a lot more popular now, but still best quality comes from class A really. So one of the things that we'd be interested in is how much sorry, just get my pointer up again. How much distortion and how efficient are these amplifiers, to give us an idea of how good they are in these different parameters that we're interested in. So we're interested in these, they're fundamental things. We would like the output of the amplifier to be a faithful representation of the input, i.e. it's linear, but as you've probably gathered by now, not everything is completely linear, and eventually as we turn the amplifier up normally, we start to get distortion as non-linearities come into play. And there's this measure called total harmonic distortion, or THD you might see it represented as, which is a measure of how much distortion there is in the signal, and it measures the harmonics of the, so you drive it with the sine wave and you measure the amplitude of the harmonics of the sine wave, and that's an indication of the non-linearity in the system. If there are no harmonics, then it's a very linear system. So we basically look at how much power is in the harmonics compared with how much power is in the fundamental, and the low number is good, so it should be much less than 1% or so is a good performance. So you can get this if you look at a sort of a hi-fi, typical hi-fi power amplifier, a few years old now, but from Cambridge Audio, which is a good name if you're into that kind of thing. They'll give you all kinds of performance figures for this, and you can see here that we've got THD, total harmonic distortion, of less than 0.01% at 1 kilohertz with 80% of rated power. So we've got the volume knob turned up to 80%. But that's only at one frequency. Now the audio range, which we would listen to, is normally classified as being from 20 Hz to 20 kilohertz. So that's what a good ear can hear, although I don't think any of our ears can now hear 20 kilohertz. Probably closer to 15 or 16 now. At 80% of rated power, and you can see that obviously it's pretty good at 1 kilohertz, but there are some other frequencies where it's not quite as good, so we're down at 0.15% across that whole range at 80% of the power, which is not bad really. But it also tells us its frequency response down to minus 3 dBs is 5 Hz to 50 kilohertz, so it actually has a fairly flat response up to 50 kilohertz, which is well outside the alleged audio range. But if you're an audiophile, you might argue that, well, actually the harmonics are interesting and they colour the sound, but I'm not convinced that that has of any use really. And then there's some other numbers as well. We've got a signal to noise ratio, which is how much noise is in there as well, which is greater than 82 dBs, which is pretty good, and then some other stuff as well. And look, in terms of efficiency, maximum power consumption 260 watts or so, but the power output is only 35 watts into the speakers. So whichever way you cut this, 260 in to 35 out, that's not very efficient. So that's just something to think about as well. So you can tell a lot from these technical specs. And this isn't a particularly expensive amplifier, and higher cost ones usually have better THD, but whether you can actually hear it or not is a different argument. So we can measure the efficiency, depends on your definitions, but we can define it as nu, or N if you like, as the load power divided by the supply power. So that's useful power over total power. So you could also define that as signal power delivered to the load, which is the useful one, and over the DC power delivered to the circuit, so the total power needed to actually run your system. So that's a definition of efficiency that we can probably work with. And then we should probably look in a bit more detail at how these things operate. So we can say that the Class A stage is very similar to a common emitter amplifier. But usually the common collector stage is preferred implementation due to its low output impedance. So it looks like there are two transistors here, but really this one is just providing the bias. So this one, because there's a fixed current going through here, this diode here, that provides us with a fixed voltage across this point. And if you've got a fixed voltage across this, the VBE of the transistor, then the transistor will provide a fixed current. So this is just a current source as a crude current mirror. So there's always this value of I flowing down here. The input signal is coming to this one. So this is looking like the emitter resistor of a common emitter amplifier, and this is our common emitter stage here. So as the signals come into here, we'll get changes in the current going down here. But the current here is fixed because this is a current source. So any variation in the current must then either flow into the load or flow out of the load through here. If this is a small current, then current has to come back through here to provide this bias current. If this is a large current through here, then only the right amount I goes down here, and the rest of it goes through the load. So that's what's going on here. We've got this fixed bias current here. Right, nothing else to say about that. And if you looked at the characteristics of this in both directions, you will start to see that we get this common collector type of stage going on. So this voltage here will always be about 0.7 of a volt less than the input voltage here, and we get a gain of 1. So this is a current amplifying stage. We just get this, and eventually we'll get to the point where the maximum output voltage here is based on the saturation voltage of this. This is as small as it can be because this is driving biggest current it can, and all the current then will be two lots. There'll be some current coming down here. Some of it will go down here, and some of it will drive the load. And that's in this part of the characteristic here. But remember, look, we've got to have 0.7 of a volt positive in this before this transistor starts to conduct, so we get a slight offset, and that's what leads to some of this crossover distortion going forward. So that's looking at this end of it, telling us what's the maximum output voltage of this amplifier is, because we obviously want to operate in this linear range as our transfer characteristic. But the interesting bit starts to happen in the negative input region when we're trying to operate in this region. You see there's two curves here, and we'll look at the reason for those two curves now. And that sort of depends on the value of the load current, of what's maximum going on there, and also the value that's been set for this bias current. Because in the worst case, the maximum current that can be pulled through here is going to be the bias current value. And if you need more current than that, it's not going to happen. So we end up with this saturated curve at this point here. And ideally what we'll try and do is we'll try and match the bias currents and the maximum load so that we intersect at this reverse saturation point here. So we've almost mirrored the top half and in the worst case conditions. So we'd like to arrange for this value IRL, which is the multiplication of the bias current and the load current, which is the worst case or best case depending on your view, needs to be at this level here for the maximum transfer of stuff here. You could have IRL down here somewhere, but it would still, the transistor would then saturate and we'd still be hitting this point here. So we try and just get it so that this IR trace matches this theoretical minimum or maximum trace depending on your viewpoint. And that's really what this is just trying to show through here. What we want to do, as I said, is just try and balance that we define the current through the bias current, which will be free to set to be what we like really, needs to be this value minus VCC, take away or offset by the saturation voltage of this transistor, which is usually about 0.2 volts or so, and then divide that by RL. So it's a simple, almost an effective application of Ohm's law in here. Tell us what's going on, and that gives us enough bias current so that the transistor saturation voltage becomes the limit, and that gives us the maximum swing because we then follow this transfer characteristic, which is as wide, if you like, or as high as it can possibly be given the values of VCC and minus VCC in this system. So that gives us our maximum swing. So under those conditions, and if we start to ignore the 0.7 volts of VBE, we just say that we actually got big voltages. So as a first case approximation, we get this kind of signal going on. So I've drawn lots of arrows on this graph to show what's happening where. So the output voltage that we're seeing is this, and it's swinging between VCC and minus VCC. This is as big as it can get. I say not allowing for saturation voltages and VBE offsets. But if you look at the current going on, so the current in this transistor over here is described by, goes up to 2I and just down to 0 when all the current is then flowing through this, coming from the load and flowing through this bottom transistor, then back up to 2I again. And remember, looking at it's averaging I at that point. So if you then start to, and you can see that the voltage, the common emitter, the collector emitter voltage across this transistor as we cycle through is ranging from 0 all the way up to 2 VCC when this is the main conducting path and this is on. All the voltage gets dropped across this transistor as this point here drops towards this value down here. So you can see we're getting quite big, well, swings of the total supply voltage across here, and we've got currents that are varying from 0 to twice the bias current. And then if you look at the power dissipated in this transistor, which is the current times the voltage across it, you end up getting this characteristic here. And the interesting thing about that is that this is a peak. So this power, VCC times I, which happens to be the peak power, follow the blue line, that's the peak, occurs when output voltage is 0, i.e. no signal, equivalent. So it's just showing that there's a maximum power is dissipated at the 0 of the output sine wave, so which is the equivalent of having no signal. So effectively under quiescent conditions with no signaling, we would get a flat line here of dissipation, which is VCCI, which is a significant amount of power. So that's our worst case. Our worst case for power dissipation happens when this transistor doesn't actually have an input signal going into it. It's just idling. And that's not a good place to be. If you think about it, that also means that this one is also in the same conditions as well, because that's going to have VCC and I flowing through it as well. So we've got maximum dissipation in both transistors going on with no signal coming in. But we can probably cope with that. But we have to think about what happens in times of fault conditions. So if we consider the extreme where RL is infinite, so this resistance here is very, very large, which is the equivalent of having an open circuit, things are different. Under these conditions, the worst case occurs when Vout equals minus VCC. And then with no load, VCE1 becomes 2 VCC, so we get 2 VCC across here. And then the power dissipated becomes 2 VCCI. And you can see that that's actually twice the amount of power being dissipated in here for an open circuit condition than if we had a loaded condition. So that's worst case. If you start putting AC signals through, then this voltage here varies a bit and you don't get so much power dissipated. But the worst case would be twice the power here. So if you design for a normal load, then you've got a certain amount of power in here. But if you forget to attach the load, which is quite easily done on amplifiers, then actually you're going to get a lot more dissipation going on in this transistor than you hope for. So you've got to design for that to be the worst case. The other extreme for a short circuit, which again is quite easy to arrange for in an amplifier if we're not careful. Positive input voltage would result in a very big current being sourced through Q1. Yeah, obviously, because it's short circuited. And although power is still given by VCCI, I at that point is uncontrolled and could be very large, and you need to protect for that as well. And likewise, that's only worrying about this, which we consider to be the active transistor. But remember, this one is also dealing with varying voltages across itself, even though there's a fixed current going through it. So there's going to be dissipation, as I've been mentioning, through this device as well. So this is where heat becomes a problem, not necessarily in normal operating conditions, but when you have some fault conditions. So we have to be aware of that. Of course, we can use current limiting that we talked about for the power supplies. We can have current foldback, or we could just have maximum current limits coming from our power supply. But you know, these are just things we have to be aware of. So going back to the efficiency then of this Class A stage, we want the load power over the supply power, and for our circuit, assuming a peak value of V coming in, the load power is going to be the RMS divided by the load resistance, which boils down to V over root 2 squared over RL. V squared over R is the power. Yeah, so RMS voltage squared over resistance gives us that, and that boils down to V squared over 2 RL. The current in Q2 over here is constant because it's a constant current source. So the power drawn from the negative supply is going to be whatever voltage you've got across here, which is VC minus VCCI. So, and current going through is I. Sorry, so we got VCCI as being the power, and the average current in Q1 when no signal comes in is also I. So the average current drawn from the positive supply is also VCCI, which you can sort of get from looking at this and saying, well, there's two lots of VCC across here, and there's I going down it, so it's going to be 2 VCCI as the power supply voltage. So therefore the efficiency becomes power into the load, which is this one here, your V squared over R effectively, over 2 VCCI. And if you start to put the maximum values for V in, saying that V can get to VCC as its maximum, then the maximum case becomes when V equals VCC. And if we do that, things start to cancel out. So you take your efficiency calculation, you start to say, well, maximum V is actually VCC, and then things start to cancel around. And if you do that, you find everything cancels out, and we end up with a maximum efficiency of 25% for this amplifier configuration. So a Class A amplifier operating at maximum signal, maximum efficiency, which just happens to be a maximum signal size, is only ever going to be 25% efficient. And when it's operating at that efficiency with huge signals going into it, we're going to have distortion, because that transfer characteristic, although it was sort of relatively straight in the middle part, flattened out when the transistor started to get saturated at either end. So we'll start to introduce some distortion, so we wouldn't want to go anywhere near those limits. So really 10 to 20% efficiency for a lower level of distortion is about the best you can get out of Class A amplifier. Excuse me. So they're not great. These are not efficient, and if you're talking about kilowatts of power going through these things, you know, you're going to have to put 10 kilowatts of power into this thing to get 1 kilowatt of useful power out. That's not great. So people try to improve this with the Class B amplifier, and this is a typical Class B common collector power stage. 2 transistors, NPN and PNP, so it's mirrored effectively. So although the last one had 2 transistors as well, one of them was configured as a current source. These are both configured as common collector amplifiers, and this one conducts on one half of the cycle, this one conducts on the other half of the cycle. It's summed at this point, and we should end up with a sine wave coming out at this point. And this is the same sort of construction as a logic gate, and sometimes people will call it a push-pull stage, because it's pushing and pulling this voltage up and down towards the rails. It's being actively driven. When the input voltage is 0, in this case here, both these transistors will be off. So there's no current flowing through it, and so instantly we don't actually have any wasted quiescent power because there's no bias currents involved. So that becomes really good in terms of efficiency. No signal in, no wasted power, which is a good place to be. But if we start to input a signal to this, once this voltage gets above 0.7 of a volt, we'll start to get some conduction through here, and we end up with the standard transfer characteristic of a common collector stage. So it's got a slope of 1, so it's got a voltage gain of about 1, but it's got an offset, it says 0.5, but it's really about 0.7 of a volt normally for a transistor, because the voltage has to rise a little bit to get this to above about 0.7 of a volt to start this transistor to turn on. Then it starts to turn on, and then we're okay until we get to the saturation voltage of the transistor across the collector emitter part. Likewise, because it's a mirrored circuit, as this voltage goes negative, and we've got a PNP here, hopefully matched, when the VBE goes the other way, negative by about 0.7 or in this case 0.5, starts to turn on, and we get the same characteristic. So we're starting to see a total characteristic that is a bit like a straight line but has this flat bit in the middle. Remember, what sort of thing we're looking for would be we'd ideally want a straight line. I believe that wants a straight line going through 0, 0. That would be our brilliant transfer characteristic. What we've got is this sort of dead zone in the middle before it picks up. If this is, this point is over here somewhere, then it's not so bad because this is a small percentage of the overall thing, but in this case it looks like it's quite significant. And what that means is that as we put our sine wave in to this kinked transfer characteristic, for this bit here we'll get no change in output. So you can see that, which basically means 0.5 of a volt either side of this, nothing happens. So it has to rise to 0.5 before anything happens, so then it rises and follows it quite linearly. Gets to about 0.5, one transistor switches off but the other one hasn't switched on yet, so you get a flat zone, and then when the input signal drops below minus 0.5 or so, the other transistor starts to conduct, and we get this thing called crossover distortion. And that, if you did an FFT of this, or a Fourier transform with this, or just measured the spectrum, you'd start to see, so if this sine wave is say 1 kilohertz, you'd get a 1 kilohertz spike, and then because we've got very sharp corners here, we'd end up with some harmonics appearing higher up, and then we're starting to get distortion, because ideally we wouldn't want harmonics, we just want the pure sine wave because that's what we're putting in, but we're generating some harmonics. And as this signal gets lower and lower, the value of this distortion becomes higher and higher relative, so we can end up with lots of harmonics, sometimes even bigger than the the one that we're interested in, and that's when your distortion becomes significant and you start to hear it. Make this sine wave bigger in the first place, then this becomes a lot less significant. Let's just put that one here so I'll just be neat. Oops, can't draw with a mouse, but I think you get the idea. Okay, so what's the efficiency of this Class B stage then? And we know it's pretty efficient when there's no signal going in, but that's not much use to us because we want to put a signal into it. So let's just assume that the crossover distortion is negligible, which will give us our best case. And again, the power to the load is going to be the same as it was before, V squared over R, or RMS of V squared over R, or squared of RMS I should say. The current drawn from each supply will be half sine waves, half wave rectified, and they will have amplitudes V over RL, where V is the amplitude of the input signal, and in the worst or best case that will be the same as the supply voltage. And the average current then drawn will be V over pi RL, and I'll show you where that comes from in a minute. And that's from each supply, so we basically double those up and we end up with the supply power being drawn being whatever this current is here multiplied by VCC, which gives us this expression here, where V is the input voltage, and in the best case or the worst case, depending on your viewpoint, can go as far as VCC, but can also go down as far as 0 if it wants to. So therefore the efficiency is then, we just got the load power, which we had the same as before, V squared over R, over the supply power, which we've just calculated, and a little bit more complicated because there's a pi involved, and that gives us, if we simplify that down to pi over 4 V over VCC. And again, when V is at its maximum, that's when it becomes equal to VCC, and if you do that, we end up with those two cancelling, and we just end up with pi over 4, and pi over 4 is 0.78, which is 78.5 efficient. So the maximum efficiency of the Class B stage, if we ignore all efforts because of crossover distortion and saturation of transistors, is 78.5%, which is still not great. That's the absolute maximum when the signal is huge. It's still only 78% efficient, and again we're going to run into distortion issues if we operate at that level, but it's better than 25%, so we're getting in the right direction. So if you didn't know where the pi came from, I'll just leave you, well, I'll put a slide in that reminds you that the area under a sine wave, you integrate it between 0 and pi and whatever, and it boils down to this. So I'll leave that for you, but I'm going to assume that you all knew that anyway. So in terms of dissipation then, or losing of energy, where does it all go? The Class B stage, we know, has very little dissipation under quiescent conditions. So quiescent conditions means that there's no signal coming in, and under no signal conditions in a pure Class B amplifier, then there's no quiescent current, and if there's no current flowing, then there's no power dissipated, so it won't get hot. But dissipation will occur when signal input is applied, and we can get the dissipated power just by subtracting the load power from the input power. So this is the useful power that comes out, this is the power that went in, so the dissipation must be, the wasted stuff is just the difference between the two. So we can take the input power, which we calculated before, and the load power that we got from V squared over RL. Remember that V is the amplitude of the input signal. So we can say that in terms of the dissipation or wastage, if you like, where does this wasted power go? This is the levels that we're interested in, and obviously varies depending on the level of the signal, and the signal will vary with time if it's a sine wave. And the whole thing is symmetric, and so half the power is dissipated in each transistor. So each transistor must be able to dissipate this power. So that's where we have to end up designing for that. So we'd like to know where the worst case of dissipation actually is, and we get this by differentiating that power equation with respect to the V, which is the size of the input signal. So depending on how big our input signal is, we can work out where power is being dissipated, either in the load, which is useful power, or in the transistors, which is less useful. So we take that equation, we differentiate it, and substitute things in, and we end up then with expressions that tell us when the maximum power is being dissipated in the device, so the transistor, and that boils down to V squared or VCC squared over pi squared RL. And we can plot that, and that tells us that maximum efficiency at this value is about 50% or so. So the efficiency at maximum dissipation, if you plot that curve, you end up with this. So you end up with a maximum efficiency of 78% for maximum going in, but for maximum dissipation in the transfer device itself, the efficiency is only 50%, and that happens at this value here. So unfortunately, this means that at sensible values of volume, if you like, you're actually dissipating the maximum in the devices. So it's operating it is least efficient at volume settings, which are probably sensible, but still 50% efficient. Okay, so we've improved it. It's not great, the sacrifice we've made is we've introduced this crossover distortion by having accrued in this area here, by remembering we've got to have 0.7 of a volt occurring here before this transistor turns on, and minus 0.7 before this transistor turns on. So we would like to try and think of a way of reducing that, because we don't like distortion. And so one thing to do is to include the device inside the feedback loop of an op-amp, with a very high gain op-amp here, because the virtual earth here will try and maintain a difference of 0 here all the time. So as soon as this starts to get into its dead zone, the op-amp will adjust its output really quickly to maintain these in their conduction regions. And this works quite well. It's a good application of feedback, which feedback acts to reduce distortion, as we know. So that's a straightforward way of doing it. But there will always be a small amount of step over going on here, because you're asking for an infinite change in, well, not an infinite change, but a change that's really quick and 0 time for the output voltage here as it crosses over. And you never quite get that, even if you've got the best amplifier in the world. And the other way, which is what leads us to this class AB characteristic, is to slightly bias the class B stage so that the transistors are at the bottom of the linear region under their quiescent conditions. So they're already biased on very slightly. So if we actually were able to apply, say, 0.7 of a volt across this point here, this transistor would be very slightly on, but ready to move instantly up its characteristic in this direction here. And likewise, if we can put minus 7 volts across here under 0 conditions, this one is very slightly on and is ready to go straight down its characteristics. So if you put those two characteristics together, you've actually squashed up this crossover distortion point, and you get it right, you get a completely straight line through here, and there's no instantaneous changes of voltage that have been hidden in there or anything. So the clever bit becomes, how do we set these voltages and then add our signal voltage to it? And this is class AB biasing, so we're just going to apply a small amount of voltage across here to get this into its linear region. And the sacrifice we'd make for that is there's going to be a small amount of bias current always running through this. So we're going to get some wastage, but we're not going to get anywhere near the wastage that we had for the class A stage when it was biased half its characteristic. So the efficiency is still very good in relative terms, and it's now going to be somewhere between the class A and the class B, and we will then also get some dissipation in the transistor, so we just have to make allowances for that if we think it's going to be significant, particularly if you're trying to work out the worst case design on these systems. And so to bias the class AB transistor, we know that this looks a bit like a diode if we think back to our whatever transistor courses we've done, and this obviously looks like another diode there. So we can actually quite simply do that by just placing two diodes in series. So we will get twice a diode drop across this, and we want twice the diode drop across here. So it's actually quite a straightforward thing to do, and then we can bias it with a current source that allows us to apply some bias current in here to get this thing up and running so we can get it going. And this is quite a good way of implementing it into IC design, because we can make a diode in an IC just by taking a transistor and connecting the third leg back to itself. So we can have a diode connected transistor integrated into this thing, and that's obviously very good because they'll have exactly the same characteristics. Also helps us with a bit of stability with temperature, because the VBE across here varies with temperature, but the VBE of this also varies with temperature, and if it's made effectively from a transistor, then they will vary the same, and we will end up with some compensation for changes in VBE, which will affect the current output. So that's all good. It allows us then to also introduce a little bit of tuning capability, because you might want to just offset a little bit to get it into the linear region. You might not want exactly the diode voltage. You might want a little bit more. And with a simple technique like this, which is called a VBE multiplier, you can actually control the voltage across here by effectively changing the value of these resistances here. So this is what tends to be implemented into actual ICs for these type of things. These resistors are integrated and are calculated to give us a bit more than a couple of diode drops to allow these to be on a little bit further, so they're well into their linear characteristics. And if you wanted to, you can put a potentiometer in the middle and bring that out and adjust that, and that's the sort of thing that's used to be used in op-amps for allowing us to tweak bias currents and offsets and things. And if you want to know how one of these works, I think you probably should have done it in the second year with probably Kushik. There's some simple calculations there that show that in fact that the voltage across here can be made to be VBE, which is the VBE of the transistor, multiplied by the ratio of the resistances here. So that's how it gets its name as a VBE multiplier. Right. So I'm sorry, I'm going quite quick through this because I have noticed that we're a bit we've gone quite slowly up to now, so I need to catch up a bit of time. But it's okay. We've got a few extra lecture slots at the end that we can use, but we have to go quite quickly. And that will lead us quite nicely onto sort of power and temperature characteristics. Because although power transistors and small signal transistors operate under the same physics, the same equations apply, the requirements to carry more current and dissipate therefore larger amounts of power means that we end up with looking at packaging and specifications and things. And as I said right at the beginning, it's a fundamental requirement that the junction temperature should be limited to between 150 and 200 degrees if you're really good for a silicon transistor. And that's why efficiency starts to become something really important for people. But it's also important to allow this heat to be removed from the junction. If we can actually get that heat away, then we can operate with higher currents going through it. So cooling is an important thing. And if we can remove the power from the transistor, or the heat from the transistor, then the transistor can actually handle more power. So active cooling, if you're into gaming, quite often people will soup up their computers with very active cooling systems around the processor to try and pull all the heat out so they can overclock it. But like all things, we can calculate what's going on, and I think at the beginning of the next lecture then we'll just quickly go over heat calculations, which you should have done with Alex, I think last year as well, but we'll run over those so we can work out the size of heat sinks and things that we need to use to dissipate the power that we've so carefully calculated, but in a rush, admittedly. Okay, so I'll see you next time, and we'll finish this off, and then hopefully can move on to the D2A stuff. Okay, bye for now.